Hi, welcome to this class on simple harmonic motion. Let us start by defining simple harmonic motion. Simple harmonic motion is a special kind of periodic motion. What is periodic motion? Periodic motion is a kind of motion which repeats itself at regular time intervals. Periodic motion is the kind of motion which repeats itself at regular time intervals. Let us look at a couple of examples of periodic motion. A simple example could be that of a simple pendulum. So if you have the bob and the pendulum oscillates, you can see that after a certain time period, the pendulum always comes back to the original position. So it goes to one extreme position and comes back to the starting point after a certain time interval. And this motion of the pendulum's bob keeps repeating. So it's a repeating movement that happens over regular time intervals. After a certain time period, the body is back to where it started from. Another example of periodic motion could be the orbiting of Earth around the Sun. Now, the Earth goes around the Sun once every 1 year. So 1 year later, the Earth is back to the starting point. So every 1 year, the Earth completes a complete orbit. So this could also be called periodic motion. And the time period is 1 year. So these are two examples of periodic motion. What we are discussing today is simple harmonic motion. And simple harmonic motion is a special kind of periodic motion. And let us see what makes a periodic motion called a simple harmonic motion. The definition of a simple harmonic motion, let us start with that and then analyze the different parts of the definition to understand what it means. Periodic motion, as I said, is motion repeated in equal intervals of time. The two examples I mentioned were the swinging of a pendulum and the orbiting of Earth around the Sun. Now, the definition of simple harmonic motion is a long one. Simple harmonic motion, or SHM for short, is a type of periodic motion where the restoring force is directly proportional to the displacement and is acting in the direction opposite to that of displacement. All the important parts of this definition are in bold and I highlighted them as well. Let us look at this definition step by step, part by part, and understand what makes a periodic motion qualify as simple harmonic motion. If we have an arrangement of this kind, where we have a wall and a frictionless surface. This is a frictionless surface. Let us assume that it is frictionless. And if I have a body of mass m here, which is connected to a spring. Now all of us are familiar with the spring, and if you leave the spring in its natural state, then it will not be stretched, it will not be compressed, it will be in its natural, comfortable state. Now, that spring is connected to the wall on one side and to a body of mass m on this side, and this body is resting on a frictionless surface. Now, this position of rest may be called the equilibrium position. This is the natural at rest position of the body. No force is acting on this body, so the body is not moving. But if I were to pull the mass in that direction and let it go, let us see what happens. If I were to stretch the spring, I have moved the spring, I have stretched the spring by moving the mass, pulling the mass here. Now what has happened is that the mass has got displaced. Remember, this was the equilibrium position. I have displaced the mass in that direction by this amount. It has been displaced. Now, it is very natural to expect that the spring is pulling the mass back in that direction. The spring is pulling the mass back in that direction. So what happens is the mass starts moving back. But does it simply come to rest here? No. The mass gathers speed and crosses the equilibrium position and goes to the other side. So what happens is this mass moves in this direction past the equilibrium position and comes over here. Remember, this is the equilibrium position. And now the spring has been compressed and the spring pushes back. So the spring exerts a force in that direction, forcing the mass to go back. So this mass begins to execute a periodic motion, back and forth and back and forth. The mean position or the central position is the equilibrium position. The spring goes to one end, turns around, comes back to this side, turns around and executes this periodic motion. And because this system is not losing any energy, there is no friction, this movement, periodic movement, will continue. Now, if you look at the definition, and I'll put it up once again. It is a periodic motion. What does that mean? It means that the movement is executed over regular time intervals, where the restoring force, now what is the restoring force in this case? The restoring force is directly proportional to the displacement. That is the definition. Let us see what it means. When the mass has been displaced in this direction, the spring is pulling the mass back in this direction. When the displacement of the body is in this direction, the spring is pulling the mass back in this direction. This force with which the spring pulls the body is the restoring force, because the spring is trying to restore the body to the equilibrium position. It is trying to bring the body back to the equilibrium position. So if the displacement is in this direction, the restoring force is in this direction. And when the body came here, the spring is pushing it back once again towards the equilibrium position. The displacement is in this direction. Displacement is the position of the body compared to the equilibrium position. And the restoring force is in that direction. You can see in these illustrations that the restoring force exerted by the spring is opposite in direction to the displacement. When the body is here, displacement is in this direction, but the force is in this direction. When the body is here, displacement is in this direction compared to the equilibrium position, and the force is in that direction. So the force is opposite in direction to the displacement. And it is proportional to the displacement. What does that statement mean? The greater the displacement, greater the force. If I were to extend the spring a little bit, then the force exerted by the spring is lower. If I stretch the spring much more and move the mass to a position here, then the force exerted by the spring becomes much higher. So greater the displacement, in other words, the more you stretch the spring in our example, the greater the restoring force. In fact, this can be captured in a very simple mathematical relationship. Now this is the restoring force. This is the displacement. The force is directly proportional to the displacement, restoring force, and is in a direction opposite to the displacement. So this would capture the relationship between the restoring force and the displacement. In fact, we can put a constant of proportionality and call it F is equal to minus Kx, where F is the restoring force, X happens to be the displacement of the body with respect to the equilibrium position, and K is called the spring constant. A simple way to understand it is, how much force does it take to stretch the spring or to compress the spring? A stiffer spring will have a higher spring constant than a spring which is not very stiff. So this is the equation between the restoring force and the displacement. So any body which is subject to a restoring force which is proportional to the displacement and is opposite in direction to the displacement will execute simple harmonic motion. And that is the meaning of this definition. So F is directly proportional to minus x. F is equal to minus Kx, where K could be called the spring constant. Now let us derive the equations that will allow us to accurately define or describe the movement of the body which is executing simple harmonic motion. Let me show this picture to you, and then we will come back to our discussion on the board. Observe the red dot. Now the red dot is simply moving around in a circular path. It is moving at a constant speed with a constant angular velocity. So the red dot is simply moving in a constant circular motion. Now what is the blue dot? If we were to take the red dot and plot only its position along the, let's say this is the x-axis. We are plotting the position of the red dot on the x-axis. So the blue dot represents the x component of the red dot. We're just showing you the x component of the red dot. And if you observe the movement of the blue dot, it is executing simple harmonic motion. It goes from one end here to the other, and it goes back and forth, and we can prove in this case that it has a restoring force which follows the law that we described earlier. The blue dot is executing simple harmonic motion. Now, if you follow what I do on the board now. Let us derive the equations required to describe in detail the movement of such a body. Remember, we were observing first the movement of a red dot. And that is our red dot, which is executing simple harmonic. This is the red dot, I'm sorry, is executing uniform circular motion. Now this is our x-axis and this is our y-axis. So if we plot our x-axis here, the horizontal line is the x-axis. When the red dot is here, if the angular velocity of our red dot happens to be omega. Now, angular velocity of the red dot, omega, which, how do we measure it? It is in radians. Then, if the red dot started from here, how far would it go in t seconds? In t seconds, it will go through an angle of omega t. So that angle happens to be omega t radians. Why? Because the speed is omega radians per second, and we are observing the red dot t seconds after it started from here. So omega t is the angle. Now let us say that this radius is A. Let's call the radius of that circle. Remember, the red dot is executing a circular motion. The radius of that circle is A. If the center is at x equal to 0, the center of the circle is at x equal to 0, where is the red dot on the x-axis after t seconds? Well, this part here, or this part here, it's the same thing, is nothing but A cos omega t. Because simple application of trigonometric ratios, you will realize that the radius of the circle happens to be the hypotenuse of this right angle triangle. This is our right angle triangle. So A cos omega t is the x component. So at any time t, this particle will be at a distance A cos omega t from the central position. All right. So its displacement at any time t is equal to A cos omega t. At time equal to t, displacement. What about velocity? What about the velocity of the body? And clearly the velocity of the body is not constant. The velocity of the body is changing. If you look at the body in simple harmonic motion, the blue dot is going back and forth, and back and forth, and back and forth. And its velocity is changing all the time. It is clearly not uniform velocity. So its velocity is simply dx by dt. The displacement x is given by that. The rate of change of displacement is velocity. So when you differentiate displacement with respect to time, you get velocity. So the instantaneous velocity at time t will be given by this is just a matter of differentiating A cos omega t with respect to time. Now what about the instantaneous acceleration? When the velocity is not constant, clearly there is an acceleration associated with the body, and that acceleration can be calculated as a function of time by differentiating this once again. This is velocity, and the rate of change of velocity with respect to time will give us acceleration. So so velocity v is this thing. So this will give us it's just a matter of differentiating the velocity with respect to time to get this. Now you can also observe that a cos omega t is nothing but x. So we can replace a cos omega t with x and write it as so these are the three expressions that we can use to calculate at any given instant in time t, the displacement, the velocity, and the acceleration of the body. Now let us look at the energy aspects of the body. The body is moving, so it has kinetic energy. It also has potential energy because work is being done against the restoring force. So let us look at this particular simulation. Now this is an illustration of simple harmonic motion. There is a spring connected to a mass, and the mass is moving back and forth. The yellow line indicates the equilibrium position. The blue arrow indicates the position or the displacement of the mass at any given time. And the red arrow indicates the restoring force. You can see two things here. The restoring force increases as the displacement increases, and it is opposite in direction to the displacement. So all elements of the simple harmonic motion definition are represented here. So force is written as minus k into x. So this is a simple illustration of simple harmonic motion. Now let us look at what happens to this body. When the displacement is zero, which means that when the body is at the equilibrium position, it has the highest velocity. Where does it have the lowest velocity? It has the lowest velocity or zero velocity at maximum displacement, which is on either end of its movement. At its extreme positions, it has zero velocity. What does it mean for the energy of the body? At the equilibrium position, it has the highest kinetic energy and the lowest potential energy. And at the extreme ends of its movement, it has the lowest kinetic energy, because remember velocity is zero, and the highest potential energy. And these are some basic aspects that you can easily remember about simple harmonic motion. So let us quickly derive the total energy of the body which is executing simple harmonic motion. So this is our situation. This is the equilibrium position. This is the displacement. This is the restoring force. So we have all the elements we need to calculate the energy of the body. This force what did we call it? We called it the restoring force. Now there is work being done by this force. Now let us say that the work done by this force, we'll call it F, in moving the body through a short distance, dx, is given by force multiplied by the short distance dx. So that is the work done. Remember, force is minus kx. So the total work done in moving the body from the extreme position to the equilibrium position could be now what is this I have written here? Work done is an integral of the force into distance, restoring force multiplied by the short distance dx, as x goes from 0, which is the equilibrium position, to a. Now, a is the amplitude of the periodic motion. When the mass gets stretched in this direction, the maximum displacement in either direction is called the amplitude of the motion. So x goes from 0 to a, and this gives us now what is this we have calculated? We have calculated the fact that the potential energy of this body when it is at its extreme position A is given by half Ka square. In fact, with a slightly different diagram, I can illustrate also the conservation of energy. If this is the equilibrium position, the body is here and here. This body is executing simple harmonic motion between this extreme point and this extreme point. This is the midpoint equilibrium position. This displacement can be called A. This displacement can be called minus A. The kinetic energy here is 0. Potential energy here is half Ka square. Even at the other end, kinetic energy is 0. Potential energy is half Ka square. What about the middle? In the middle, the kinetic energy is the highest, potential energy is 0. But because of conservation of energy, the entire potential energy here is converted to the kinetic energy of the body at the equilibrium position. So the kinetic energy of the body becomes half Ka square, and the potential energy of the body at the equilibrium position is 0. So this is how the energy of the body consists of potential energy and kinetic energy. At the two extreme ends of the body, of the movement of the body, the potential energy is the highest. Kinetic energy is 0 here, is 0 here. But at the equilibrium position, the kinetic energy is the highest and the potential energy is 0. What about some midpoint here? What about any point here or here or here or here? Well, at those points, the energy of the body is a combination of kinetic and potential energies. But remember, the sum of the kinetic and potential energies must always equal to or add up to half Ka square, because that is the total energy of the body. So this is a short discussion on simple harmonic motion, how we can use, how we can define the movement of the body executing simple harmonic motion, which we did a little earlier, and how we can calculate the total energy of the body executing simple harmonic motion. So as usual, we will be giving you several practice question papers. And those question papers will consist of formative assessments after each topic, summative assessments at the end of the chapter, board exam papers for practice, as well as practice papers from competitive exams, all of which will be available to you. I will give you a sample of these papers, which will be uploaded to our portal as soon as the class is over. Kindly take a look at it. Here is a sample of the paper. So it will consist of multiple choice questions as well as short answer types and long answer type questions, all of which will be given to you. We will discuss some of these exemplar questions in the later class. Thank you for watching. I hope this session was useful. See you in the next class.